Hello students, I welcome you in today's session of physics, and in physics you can see here I am going to present you the chapter number 31, which is your conductor, insulators and semiconductors. Clear? So this is the chapter we have to discuss, but before going to start the chapter, just have a look what we have to study in this chapter. We have to discuss about the energy bands in conductors, insulator and semiconductors, and its qualitative ideas only. So first we will talk about the conductor, insulators and semiconductors. I hope you are familiar with the conductor, insulators and semiconductors. Conductors are those which can easily allow electricity through pass through them. Clear? These are known as the conductors. And then one thing is written here: conductors have a large number of free electrons which act as a charge carrier, while insulators have practically no free electrons. That's why insulators doesn't offer electricity to pass through them, while conductor can allow electricity to pass through them. Now come to here, you can see that the temperature coefficient resistance of conductor is positive, that is their electrical resistance increases and their electric conductivity decreases with the rising temperature. As you increase the temperature, their resistance increases while their conductivity decreases, because there is a inversely relation between the conductivity and resistivity. Now come to here, this one. There are however certain solids whose electrical conductivity is intermediate between the conductors and insulators. They are called as the semiconductors. Fine. Means they are not a fully conductor, not fully insulators. They, like carbon, silicon and germanium, are few examples of semiconductor. So in semiconductors, the outermost, that is the valence electron, are neither so rigidly bound with the atom or an insulator, nor so loosely bound as in the conductor. The temperature coefficient resistance of the semiconductor is always negative, because that is their electrical resistance decreases or conductivity increases with the rise in temperature. So at absolute zero temperature, a semiconductor become an ideal insulator. This is the most important one, at which temperature the semiconductor start behaving like an insulator. So at absolute zero. Now you can see here, this is the energy band. We will discuss about the energy bands. Just see this figure. This is the energy band. So a solid contains an enormous numbers of atoms packed closely together. So each atom, when isolated, have a discrete sets of electrons energy. Clear? Name as 1s, 2s, 2p, 3p. This thing you had already studied in the chemistry. So if we imagine all the n says atoms of the solid to be isolated from one another, then they would have completely coinciding sets of energy levels. That is, each of the energy levels of this an atom system would have an n-fold degeneracy. The electron fill the energy levels in each atom independently as the atom approach one another to form the solids. A continuously increasing interaction occur between them, which causes each of the level to split into n distinct levels. So in practice, however, n is very large, that is 10 to the power 23 cent per centimeter cube. Therefore, the split energy level becomes so numerous, so close together, that they form an almost continuous energy bands. You can see this is the energy bands. So the amount of splitting is different for different energy levels. So in general, the lower level are split less than the higher levels. The lowest general level remaining almost unsplit. The reason is that the electrons in the lower energy level are the inner electrons of the atoms, which are not significantly influenced by the presence of nearby atoms. On the other hand, the electrons in the higher energy levels are the valence electrons, whose wave function overlaps appreciably. So in the figure number 1 shows the formation of energy bands for some of the higher energy levels of isolated sodium atoms, whose ground state configuration is 1s2, 2s2, 2p6 and 3s1, and their interatomic distances decreases. The dashed lines indicates the observed interatomic separation in solids. Here you can see this in the figure. Now the 3s and the first occupied level to be split into the bands, the 2p level, do not begin to split until the interatomic distances become smaller than actually found in the solid sodium. The levels 1s and 2s do not split at all. Fine. Now the energy bands in a solid correspond to the energy level in an atom. An electron in solids can have only energy that fall within the these energy bands. So the various energy bands in a solid may or may not overlap depending upon the structure of the solids. So if they do not overlap, then the intervals between them represent energies which the electrons in the solids cannot have. Fine. So if they don't overlap, you can see the figure number 2 and figure number B. The interval between them represent energy which the electrons in the solid cannot have. So these intervals are called the forbidden bands or the energy gaps. If however the adjacent energy bands in a solid overlap, then the electron have a continuous distribution of allowed energies. The energy bands formed from the atomic energy remains containing valence band electron is called the valence band. An empty band above the valence band into which the electrons can pass is called the conduction band. Here you can see this is the valence band and the conduction band. This is the forbidden band. Clear? Now classification of solids into conductor, insulators and semiconductor on the basis of energy band structure. So we will classify how we can classify them. So metals are good conductor of electricity. Insulators do not conduct electricity, while the semiconductors hold a conductivity intermediate between that of conductor and insulators. So the distinction among solids can be explained from the energy band structure. In general, an energy band of a solid having capital N atom has the total n energy levels, and each level can hold 2 multiplied by 2l plus 1 electrons corresponding to the two different orientation of the electron spin and 2l plus 1 orientation of electron orbit angular momentum. Thus, the electron capacity of the band is 2l plus 1 multiplied by n. It means that the 1s, 2s, 2p, 3s bands can hold 2n, 2n, 6n and electron respectively. The classification of solid into conductors, insulators and semiconductor is based on the nature of the bands occupied by electrons. Clear? And the width of forbidden bands, energy gaps. Now what are the conductors? You can see here in some solid there is a partially filled band above the completely filled lower band. Such bands is formed with the partially filled atomic levels, as in case of alkali metals like sodium. So a sodium atom has a single valence electron in its outer level. Therefore the n atoms in a solid piece of sodium each contribute only one 3s electron to the solid, and so there are only n valence electrons in the 3s band. So the valence band 3s thus only half full. Here you can see the valence band, this is the conduction band, and this is the forbidden energy band. So a partially filled bands may also be the results of overlapping of completely filled band and an empty band, and in case of alkaline earth metal in figure 3b you can see here are shown the energy bands of beryllium, in which there is an overlap of the lower energy levels of the empty 2p band with the upper energy levels of the completed 2s bands. So those electrons which would occupy the highest energy levels in the 2s band will actually go onto the lowest level of the overlapping 2p band. These levels at the top of the 2s bands become unoccupied and the band is only partially filled. Clear? Now you can see here, now suppose an electric field is applied across a piece of a solid sodium or beryllium, then electrons in the partially filled valence band can easily acquire the additional energy to move to the higher occupied energy levels within the same bands. Clear? So without crossing any energy gap, the additional energy in the form of kinetic energy and moving electrons constitute the electric current. Fine. So here you can see this is the conduction band and there is a valence band and there is a forbidden gap which is 7 electron volt. Now come to the insulators. So what is the insulators? I told you, which do not allow electricity to pass through them. So in some solid the valence band that is containing the outer electrons of the atoms is completely filled, while the next higher bands separated by the energy gap of a few electron volt is completely empty. So such a solid is called an insulator. So diamond and sodium chloride are typical examples of insulators. Now see the figure 4. This is the figure number 4. The energy bands of diamond, there is an energy band completely filled with electron valence band, and above it is an empty band, that is the conduction band. Fine, which is separated by 7 volt. The band below the valence band are also completely filled. Here you can see this is the valence below the conduction valence band. So at least 7 electron volt of energy must be provided to an electron in the diamond crystal in order to enter the conduction band where it can move freely. So with the kinetic energy of 0.025 electron volt at room temperature, and the valence electron do not have enough thermal energy to cross the 7 electron volt gap. Now if an electric field be applied, the electrons in the valence band would not accept energy to move within the band because there is no occupied level in this band. So they can, however, move to the higher empty band provided that they get energy of about 7 electron volt to cross the gap. Now since the electric field cannot give this amount of energy, so the electron do not acquire a directional motion. Diamond is therefore an insulator. Now we will discuss about the semiconductors. So certain solids have the basic crystal structures of an insulator but with much smaller energy gap of the order of an electron volt between the valence band and the conduction band. Such solids are known as semiconductors. So like germanium and silicon are the semiconductors. They having energy gaps of 1.1 electron volt in silicon and 0.7 electron volt in germanium. These are the typical examples of semiconductors. Now figure number 5 shows the energy band of a silicon. So at room temperature, a few of its electrons in the valence band have sufficient kinetic energy or thermal motion to cross the narrow energy gap and enter the conduction band above it. Hence, when the electric field is applied, the few electrons present in the conduction band acquire additional energy to move to the unoccupied level within the same band. Similarly, a few of the many electrons present in the valence band move to the few many electrons present in the valence band move to the few unavailable occupied levels in the same band. Hence, there is a limited flow of the current across the crystals. The silicon has an electrical conductivity intermediate between those of conductor and insulator, and therefore it acts as a semiconductor. Now there is a electron and a holes. This thing I am skipping because you know very well what are the electrons and holes. Now I am coming to the intrinsic and semiconductor. What are the intrinsic semiconductors? So a pure semiconductor which is free from impurities is called an intrinsic semiconductor. You can see here, and its electrical conductivity which arises by the thermal excitation of electrons from the valence band to the conduction band is called the intrinsic conductivity. Now pure germanium and pure silicon are important examples of intrinsic semiconductor. Their electronic configuration you can see here, and what the mechanism of electrical conduction in an intrinsic semiconductor you can see here. So an atom of germanium or silicon has 4 valence electrons surrounding an inert core nucleus. These materials consist of a 3-dimensional tetrahedral pattern with an atom at each vertex. So this is illustrated in the 2 dimension. You can see here, this is the figure. So each of the 4 valence electron of an atom is shared by an electron of its 4 nearest neighboring atom. The covalent bonds so formed, shown by the dashed line, provided the binding forces between the neighboring atoms. Fine. So at temperature closest to absolute zero, all the valence electrons are tightly bound to the core, are all said to be in the valence band, and so no free electrons are available to conduct electricity through the crystal. Now at room temperature, however, a few of the valence electrons are thermally excited into the conduction band. In that cases, the excited electrons leave hole in the valence band. So higher the temperature, larger is the number of electron hole pair produced. So when an electric field is applied to the crystals, the free electrons in the conduction band move into the direction opposite to the field, and the holes in the valence band move in the direction of the field. So both giving rise to the electric current. Clear? So this motion of the holes, however apparent, it is in the fact that the motion of the otherwise bound electrons from one vacancy to the next within the valence band is a direction opposite to the applied field. Thus, in a semiconductors, electron and holes both constitute currents. The total current is the sum of the two currents. So although the number of free electrons in the conduction band is equal to the number of holes in the valence band, so the electrons contribute to the current is larger. So this is because the free electrons in the conduction band move easily bound electron in the valence band, which causes the motion of the holes. Fine. So the conductivity of an intrinsic semiconductor is very poor. At ordinary temperature, only one covalent band breaks in 10 to the power 9 atom of germanium. It means that only one atom in 10 to the power 9 atom is available for conduction. Thus intrinsic semiconductor have no practical utility. Clear? So thus in a semiconductors, electron and holes both constitute currents. The total current is the sum of the two currents, although the number of free electrons in the conduction band is equal to the number of holes in the valence band. Thus the electron contribution to the current is larger. So this is because the free electrons in the conduction band move more easily than the bound electron in the valence band, which causes the motion of the holes. Clear? That is, the conductivity of an intrinsic semiconductor is very poor unless the temperature is very high. So at ordinary temperature, only one covalent bond breaks in 10 to the power 9 atom of germanium. So it means that only one atom in 10 to the power 9 atom is available for conduction. Thus intrinsic semiconductor have no practical utility. Concentration of free electron and holes in intrinsic semiconductors. So in an intrinsic semiconductor, the concentration number per unit volume of electron in conduction band and that of holes in the valence band are equal at a given temperature. Thus if Ne and Nh be the electron concentration and hole concentration respectively, so we can write it Ne is equals to Nh equals to Ni. That is, Ni is called the intrinsic concentration or intrinsic charge carrier density. So for germanium, Ni equals to 2.4 in 10 to the power 19 per meter cube, and for silicon this is equals to this at room temperature 300 Kelvin. Now what is the effect of temperature on the conductivity of pure semiconductor? This is the important one. The conductivity of the pure semiconductors increases or the resistivity decreases with the rise in the temperature. This is because as the temperature rises more and more, the covalent bond in the crystal lattice breaks, thus creating more and more charge carriers, that is electron hole pair. So this results in increasing the conductivity. Fine. Now the temperature dependence of the charge carrier density is given by, this is the important formula, so just remember this, Ni is proportional to e to the power Eg by 2 kT, where Eg is the energy gap of the semiconductor, K is your Boltzmann constant, thus the charge density and hence the conductivity of the semiconductor increases exponentially with the rising temperature. So that's all, student, for this lecture. The extrinsic semiconductor we will discuss in our next lecture, that is lecture number 2. Till that, do study. Thank you, class. Thank you.